So for collisions, we can go into our pop network and put a static object in. And there it is, static object. This is a strange node that says static object, but you can actually totally use it for things that are not static. Should probably change the name, but what are you gonna do? So connect it into our sim by putting it into our merge here. Let's have our, I'm gonna put it as my leftmost input because at least by default the merge says left inputs affect right. So we usually put our colliders on the left. I mean, you could change it to mutual and then you could put it anywhere, but as a force of habit, I always like to have my colliders be on the left. At any rate, this needs to point to our collision geometry. So I'm going to say, let's use that facade thing that we've been talking about a lot. So if we go back to our the rigids thing here in our particles area, click this arrow to remind ourselves what that is. Space G to center on it. And again, that's what we had imported here. We had merge in proxy facade, and then we input a null. And there it is. Okay. So there it is. So it's pointed to, and technically, that's really all you should need to do. If I put use deforming geometry on, well, if you just play it, it will just be a static thing. By turning on use deforming geometry, it will mean it will actually allow it to move. What static object is trying to say is it won't be affected by a simulation. It will only affect one. So if you want it to be moving, it can be. It's still considered a static object because it's not being affected by a simulation. Here's the problem though. If I put the dynamics flag export back down to here, meaning evaluate the whole network, don't just evaluate this, this simulation is still going to be very, very fast. And as nice as that would be, it means more often than not that something's wrong. If you look at our points coming through the wall here, that should confirm it to us. It's not working. What's not working is that the static object itself is not creating collision, anything to collide against. Because by default, the way the static object works is it wants to create an internal volume to be collided against. This isn't a volume like, smoke or anything. This is going to be a sign distance function, which I don't think we have talked about yet in the volume series, but if not, here's a little demo about it. So here we are. I want to talk about sign distance functions because it comes up a lot in this lesson, almost always, I think, for collisions. So what are sign distance functions? They're kind of volume. And until now, we're used to talking about volumes that look like this. Density volumes, also known as fog volumes. They basically take something and then they're representing that something as density values. Maybe from 0, meaning there's no density here, to 1, meaning there's full density, or maybe even higher than 1. It could be 10 density. But in any case, the voxels simply represent how much stuff is in it. Sign distance functions don't do that. Sign distance functions represent geometry as a volume. So that's why they even kind of look like that. How does it do it? Well, the voxels in this volume are storing how far they are, how far that given voxel is to the surface, to the closest surface rather, of the model, of the mesh that used to be there. So if you look at a slice of it like this, we have a visualizer for this volume, and we can see when we're out here where it's red, there's high values being stored. And when we're inside, it's blue, there are low values being stored. Because by default, at least, that's how SDFs worked. That's the signed part, the S. Negative, meaning the negative sign, means that we're inside of it. And a positive, meaning a positive sign, means we're outside of it. And right around here, as you can imagine, where transitions from negative to positive is 0. And that is where it considers the actual surface to be. So the way it's showing us in the viewport is it's showing us, again, as if it is a model. But really, there's values everywhere that are all just saying how farther and farther and farther they are away. Now, they're called SDFs here for Houdini's native volumes. For whatever reason, the VDB form, the other more memory efficient way of storing a volume, where we don't store values away from the surface, that's basically saying only store the values 3 voxels from the surface in either direction, both exterior and interior to it. So if we look at that one instead, it'll kind of look like this. I mean, it's still storing the same general idea. It's just that this one never stores values so deep in here that it gets as dark blue as the Houdini one, the native Houdini one, which is storing values all the way in. So to prove that point, I can increase the interior band. I can store deeper and deeper values into it like so. I can store more and more values out here. But it's mostly redundant. We don't usually need all that extra stuff, and VDB knows that. It's still representing the surface just fine. Because that's the whole idea of the sign distance function. All we need to know usually is if we sample the space in here, is it negative? We're inside. Sample it out here. Is it positive? We're outside. Very quick and easy collision detection. So that's what we're talking about when we're talking about sign distance functions, even though VDB calls them a distance VDB instead, or sometimes a surface VDB. It's the same as an SDF. So back to the lesson. So back in this, what that's going to look like is actually, you can visualize it here under collisions. And even though it says RBD solver, just ignore that. It doesn't really matter. The point is, if we look at collision guide, we can see it. Turn off display geometry and let's take a look at it. Well, I don't actually see anything, which is part of the problem. So the main reason why it's not working is because, once again, this is packed geometry. It just doesn't work. So let's say we did do the unpack and then trail. So now it's polygon geometry. That should work, at least. I mean, as you can probably tell from the tone of my voice, it's not going to work either. But I'm going to copy the trail because I want the path to it later. Come back in here, put that here instead. So what happens? I should see something. Let's actually turn off, or rather, let's just look at it. I don't see anything. I should see a collision geometry. I should see that volume. The problem is that the divisions here aren't high enough. This is divisions of the voxels in the collision geometry that it itself is creating for us. The problem is that, these walls are very thin. If this was a big, like, pig head or something that we could get away with it, that would be one thing. But look how thin these walls are. Everything in here is thin walls. It's the worst case scenario for this node, pretty much. I can go up to 100. That's not too bad. Now if you press play, you can see it's getting slow. This is not the particle sim. This is just the creation of the static geometry here. And it's still not thin enough. We still don't see anything, really. Now I go to 200 divisions. And now see how long it's taking? Now we're starting to see something that's decent, but there's still so many holes in the wall. It's not great, and it's really slow now. This is now pretty much just unacceptably slow. It's just too much. And it's still, especially considering that it's still not even that accurate. You'll still get points flying through here. So that pretty much leaves us with 2 options. This won't work, clearly. But we do have 2 options. The 2 options are, we can either create the volumes for this node, so it doesn't have to use its old-fashioned, not very good way of doing it, or we can say don't use volumes at all. Use surface collisions. Let's start with volume collisions, though.